Hi friends, I am Khan sir and you are watching my YouTube channel Physics with Khan sir. Today I am going to discuss a very important topic of physics which is a part of the chapter current electricity, and the problem that arises in many ex- exams, or maybe the MBBS NEET exam all India, or the triple exam, or JEE main, and any UG physics also. That is a very popular and common problem. You all heard about Wheatstone bridge, and this bridge is one of the basic elements found in many electrical network circuits. Okay, so basically in power supply circuit, almost all power supply has a rectifier, and that comes as a bridge circuit. Okay, bridge rectifier. So I will start with a specific problem. And as you know that a bridge circuit, Wheatstone bridge, has four arms representing four resistances, and there we need a power supply and and a load to be connected. And so, what are the requirements? First of all, we need a power supply or a battery, source of EMF. We need a load resistance and four resistance representing four arms of the Wheatstone bridge, and some connecting wires. And for measurement we need a voltmeter and ammeter, and to make and break the circuit we need keys. Okay, so these are the few elements we required to do experiment and theory with the Wheatstone bridge principle. So let's see the problem first. Okay, here in the diagram you can see that we are given a circuit which has four resistances: 5 ohms, 10 ohms, 15 ohms, 20 ohms. This four resistance makes the Wheatstone bridge. Okay, so our objective is to find the current in the branches. That is, this is the battery, and the current starts from the higher terminal and goes through the network and returns to the negative terminal of the battery. So in this, at the junction A, it is divided into two components. One passes through the 5 ohm resistors, that is say I1, and other passes through the 15 ohm resistance, say I2. And there is a point C, the another network is there. The resistance between C and D is corrected as 100 ohm, and let the current be I3 through that branch. Clear? And this current, this I2 and I3, are added up here and passes through the 20 ohm resistance, and which added again to the resistance current I1 that flows through the resistance 10 ohm. Okay, this may be I1 minus I3, and this is actually I2 plus I3. So the total current is again I. Our objective is to find the potential of the point A, potential of the point B, potential of the point C, potential of the point D, current I1, current I2, current I3, and the total current I. This is our objective. We also want to find the effective resistance between the point A and the point B, right? And also the resistance between C and D, which is given. Actually, we want to know the potential difference between point C and point D. Clear? So this is our objective. Let us before going to solve the problem directly, we shall derive a general formula to solve the problem with with following definite steps. So first of all, we draw a general circuit comprising four resistors, say R1, R2, R3, R4, and a battery of EMF E. So this can be drawn here in this way. Suppose this is resistance R1, this is resistance R2, this is resistance R3, and this is resistance R4. These are connected. So what we talk, this is our R1, this is R2, sorry, say this is R3, this is R2, and this one is R4. And this point, say this point is C, and this point is say D. And the battery is connected between the point. This point is A, and the bottom point, this is B. And the battery is connected here. The aim of the cell is, this is at higher terminal potential, this terminal is at lower potential. So the current starts from this point, from the battery at the higher terminal, flows through this wire and reaches here. Here it is divided into two parts. This is I1 and another part flows in this path, I2. First of all, we shall not correct this one right now, and this current I2 and I1 again meet together at the junction and returns to the battery as the total current I. Let us first analyze this part. First of all, we say, let us look what is the voltage at this point. This is important to understand. Most in electrical circuit analysis, we basically take the negative terminal to be at 0 volt. This is compared to the ground. So the potential at the point B, which is connected to the negative terminal of battery, should be taken 0, and the potential of the other terminal, that is terminal A, should be the potential of the or EMF of the battery cell E. So that means if we move from the bottom to the upper terminal, the resistances in this RM increases, so the voltage will increase, right? And which is the maximum voltage will be at the point E, which is the potential of the positive terminal of the battery. Same argument is valid for the right arm also. Here also the voltage is 0, potential at this point is 0, and if you go upward, the potential will increase, and here we will get the maximum potential or the potential of the cell, right? So first of all, we can calculate the currents in the branches, that is, what is current I. So say VA is how much? VA is E, and what is VB? VB is 0. Clear? So the current in the left branch I1 must be the potential difference between the points A and B, that is VA minus VB over the total resistance of this branch, that is R1 plus R2. So this much current flows through the branch containing the resistance R1 and the resistance R2. So this is nothing but what is VA? VA, as we know that VA is E, this is E over R1 plus R2, since VB equal to 0. In the same footing, we can have I2 equals how much? The potential difference between this point is VA minus VB, and the total resistors, the R3 and R4 are connected in series, so the effective resistance is nothing but, we can write VA minus VB over R3 plus R4. Clear? So this is again E over R3 plus R4. Clear? So now I want to find the potential of the point C and the potential of the point D. What is VC? VC you can write, this is the current in this branch is I1. So the potential drop across the resistance R2 will give the potential difference between the point C and the point B. That means VC minus VB must be I1 times R2. This is nothing but Ohm's law. Ohm's law is this is the 2 points of the circuit, but the current is I1 and the resistance is R2. So the potential drop must be I1 R2. This gives us VC minus 0 equals E over, let us keep it as such, I1 over I1 times R2. That means VC is our I1 R2, which is nothing but ER2 over R1 plus R2. So this is VC. So we got VA, we got VB, we got VC, and now I want to find VD. So what is VD? Very simple. VD is how much? We shall take this, the potential difference between this point D and the point B is VD minus VB, which according to Ohm's law is nothing but I2 times R4. I2 times R4. So and again so this is VD minus 0 because VB is 0, because this is grounded. So this is I2 R4. Hence we have VD equals I2 R4, and you know that I2 is nothing but E over, I2 is what? E over R3 plus R4, and this is R4. So we got VD. So we have found out the current I1, current I2, voltage VA, voltage at VB, potential at C, and potential at D. So these parts are solved. This one, this one, this one, this one, this one is done. Clear? So if we want to summarize, then we can write it here. I1 equals E over R1 plus R2. I2 equals E over R3 plus R4. VA equals E, VB equals 0, VC equals this, can write VC equals ER2 over R1 plus R2, VD equals ER4 over R3 plus R4. So these are the expression what we got from this general diagram. Clear? Now I want to find the potential difference between the point C and the point D. So what is VC? This is VC minus VD. Clear? So this is nothing but ER2 by R1 plus R2 minus ER4 over R3 plus R4. So we can take E outside. So this is R2 over R1 plus R2 minus R4 over R3 plus R4. What is this? And if the resistance connected between C and D is represented by RL, and if there is a current through that RL which is represented by IL, then we can write this, okay? Or since, or according to the circuit, since the resistance connected in this branch is say R5 and the current here is I3, we have I3 R5. Clear? So the resistance of this branch is R5 and we have suppose the current is I3, then according to Ohm's law, the potential drop across R5 should be the potential difference between the point C and the point D, right? So this is given by this. So what is I3? Now we can write simply I3 equal to E over R5 times this quantity. Clear? So we got everything. Clear? So we got I1, we got I2, we got I3, and finally we want to see what is I. The total current I is nothing but I1 plus I2. This is from the principle of the charge conservation. According to charge conservation, the quantity of charge that enters this terminal are divided into two branches. So the net charge at any time at this point A should be 0. There will be no accumulation of additional charge at any point. So at each junction the total current must vanish. That is, algebraic sum of the current should vanish. From that concept, that is called the Kirchhoff's current law, we can write this very simply, straightforward. So this is how much? This is, we have already the expression for I1 and I2, so you can directly write it this way. This is 1 over R1 plus R2 plus 1 over R3 plus R4. So this is our total current. So one by one we got all expressions. That is our target problem. We got the potentials of each junction A, B, C and D, the potential difference between the points C and D, the current I1 and the current I2, and also the current in the branch, middle branch that connects the point C to the point D. In Wheatstone bridge circuit, this resistance R5 is represented by galvanometer. Okay, so between C and D we connect a galvanometer, and between A and B we supply the connect the energy supply or the source of potential. Battery is connected. So we have all the necessary calculations. Now, if I want to find the effective resistance between A and B, then we can have it, see the total current between the branch between the point A and B that flows from the point A to the point B is I, and the EMF connected to the two terminals is E. So the effective resistance must be E over I, right? So that can be estimated simply as we can rub this one. Okay, so this is, if we calculate VA minus VB, then we'll get a total current I and the total resistance say R, which represents AB. This is the effective resistance between the point A and B. So this is the total current and this is the total resistance. This whole network, when excluding this network, when replaced by a simple resistance, single resistance, that would be represented by AB. Clear? In the open, when C and D are open, then there will be no flow of current through R5, so this is not connected. So in the open circuit condition, and if this terminal C and D opened and say battery is shorted so that the EMF is 0, then the circuit is left only with the 4 resistances between the points A and B. So the effective resistance that is should be measured between points C and D should come out as the combination you are looking here. So the resistance between the point, there are two branches, this branch and this branch, these are in series, this is also in series, they are connected in parallel. So the total resistance must be I equals how much? This one is I. So we can also have it from here. VA is E, VB is 0, I is this given by this expression. So this is E times 1 over R1 plus R2 plus 1 over R3 plus R4 times RAB, right? So on the left side we have E minus 0. So if this E is 0 is removed, we are left with 1 equal to this one, RAB times this quantity. Okay, so finally we get RAB, 1 over RAB equal to 1 over R1 plus R2 and say that, okay, I shall write it here. Okay, so one by one we got all expressions required. So this is RAB. The RAB is nothing but 1 over you can calculate it, see from here. So this is RAB. RAB is how much? This is not required. Sorry. So from here, okay. So this RAB is nothing but 1 over 1 by R1 plus R2 plus R3 plus R4, right? So this is the expression for RAB. Clear? RAB times this equal to 1, so RAB must be 1 over this. Clear? Now, since we have got all the necessary formulas, we can now solve easily all the components. First of all, we shall find that VA, according to this diagram, the potential at this point must be the potential of the EMF E. So VA equal to E equals 10 volt. So first part is done. Second, that we wanted VB. VB is how much? This is 0 volt. This is the negative is taken as ground. What is VC? VC is, from this circuit we get ER2 over R1 plus R2. So what is E? E is 10 volt, right? And R2 is the current in the branch. R1 ER2. So this one is actually 10 ohm is our R2. This 10 ohms is the R2. This is I1 R2. So this must be 10 times 10 in the EMF. Another 10 comes from this resistance, and we require the total resistance in this branch, that is nothing but 5 plus 10. So the unit is, we are taking VC, that must be volt. Clear? So this is how much? 100 over 15 volt, which equals how much? 6.68 volt. So we got VC. Clear? So VC is 6.6. So VA, VB, VC is obtained. Now we can calculate VD. So according to our formula, VD, the potential at this point is how much? The potential E over E times the resistance R2. Okay, so this is R4 according to our diagram. This one R1, R2, R3, R4. So this is R4. R4 is nearer to the negative terminal of the battery. Okay, so this is R3 plus R4. If we put the numerical, then we will get 10 volt. R4 is how much? R4 is 20 ohms. 20, and here R3 plus R4 is 15 plus 20. This is volt. So this is how much? So on the numerator we have 200, and the denominator we have 35 volt. So we will get actually 35 over 20. That means this is nothing but, if we take 40 over 7 volt, so this is nothing but 5, sorry, clean the board. Okay, so this is 5.55, and if we rounded to 5.56 volt. Clear? So we got I1, I2, sorry, VA, VB, VC and PD. All potentials of each point is now calculated. So next we will calculate I1. Oh, what is I1? I1 can be calculated straight from here. So I1 is, so we got VD equal 5.56 volt, right? So what is I1? I1 equals E over R1 plus R2, that is 10 over 5 plus 10 ampere, and this is the A. Ampere is simply write A. So 10 over 15 means 10 over 15 means 0.66, right? 66A. Here, approx. Similarly, I2 is E over R3 plus R4. We have the expression for that, I1 and I2. Using those, from I2 is E over R3 plus R4. So we can calculate this as 10 over 15 plus 20 ampere. That means 10 over 35A. So this is 2 over 7. This is 2 over 7 means how much? 2 over 7. 5 2s, 5 7. So 2 over 7 amps equal 0.285 ampere. Clear? So we got I1, I2, and now we can have the total current I, which is the sum of the individual branch currents I1 and I2. So we have all the results. So I1 is calculated, right? Lungi choda sone. So this is I equal I1 plus I2, that means 0.66 plus 0.28 ampere, that is 0. How much? 94 ampere. This is the total current in the circuit. Clear? So this bridge, as it is seen that the potential at the point C and the potential at the point D are not same. VC is how much? 6.68 volt and VD is 5.56 volt. So the bridge is unbalanced and there is a flow of current from the point C to the point D, and the current can be calculated because the resistance R5, which is 100 ohm, is given here. Okay, so we can calculate I3 also. So how much is I3? I3 is, E means 10, R5 is given as 100 ohm. So, and this quantity within the bracket is, that is comes from the VC minus VD, and VC was E over R2 over R1 plus R2 minus R1 R2 over R1 plus R2 minus R4 over R3 minus R4. So the R3 plus R4. Okay. So actually this one is VC minus VD, and we had VC minus VD. So we may also remove this or put directly the resistance, no problem. So E is known, R5 is known, everything is known. So we can have this as 0.1 times actually okay. So this can be okay. I am simplifying. This is nothing but VC minus VD over VC minus VD over R5. This one is more easier. So what is VC? VC is 6.68 volt and VD is 5.56. R5 is 100 ohm. So this is this much ampere. So how much? This is nothing but 0.12 over 100 ampere, and this is approximately 1.2 times 10 to the power minus 3. Okay, this is 1.2 times 10 to the power minus 1. So this is minus 3 ampere. So the current through the branch is 1.2 milliampere, right? So we have all components which we have intended to discuss here. Clear? We are given 4 resistance circuit as shown in this diagram. We step by step calculate the potential at the point A, which is nothing but the EMF of the cell 10 volt. Potential at the point B, which is taken as the ground, so it is at 0. Potential of the VB is 0. We calculated the potential of the point C, which is the potential drop across the resistance of 10 ohm due to a current I1 flowing in this branch. So that is calculated as this is 6.68 volt. Again we calculate the potential of this point D, which is the potential drop across the resistance 20 ohm due to the current I2 in this branch. So that gives we got it as 5.56 volt. We then calculated the currents I1 and I2 using the expression. This is the EMF, the VA minus VB over sum of the resistance of this branch. So we will get it as 0.66 ampere. And the current of this branch, this is at the high resistance, this branch has a high resistance, so the current definitely will be smaller. So this is lesser current flows through this branch. This is 0.28 ampere. So the total current in the circuit is 0.94 ampere, and the effective voltage between the points A and B is effective to 10 volt. So that effective resistance between A and B must be 10 over the current 0.94. That is something more than 10 ohm. So if we calculate the resistance, we can also calculate it from here, but this one is more simpler as we know the total current. So this is nothing but E over RAB, E over R effective. Okay, E over this is the total current I, E over I. So this is how much? 10 over 0.94 ohm. Okay, so this is approximately something greater than say 11 ohm. Okay, so the effective resistance of this network is 11 ohm nearly, which is less than both the branch resistance. This is 15 ohm and this is 35 ohm. So they are in parallel. So the effective resistance must be, or the parallel equivalent resistance must be less than each of them, or that is less than the lower potential, that is 15 ohm. So this is 11 ohm. Okay, clear? So we discussed every components of this circuit. Since the whiteboard is very smaller in size and the write-up was clumsy, but if you follow step by step, it will be clear to you. So before concluding, we can again recapitulate the main concepts. So to analyze a Wheatstone bridge circuit which have 4 resistances, we may connect it this way. We have to take the EMFs and the negative terminal to be treated at grounded or 0 volt. Anything, this one is R1, this R2, R3, R4. What is the EMF of the battery is E. So what is the voltage at this point? Potential of this point is 0. Potential of this point is the potential of the positive terminal of the battery. So the net effect potential between this point was actually A, this is B, this is C, and this is D. So the potential between A and B is taken as the EMF of the battery, and the branch resistance total, this resistance R1 and R2 in series. So the effective current that flows through this branch is the EMF E divided by sum of these resistances, that is current I1. So I1 is nothing but E over R1 plus R2. We have calculated this. Similarly, same footing, if you look that side, now forget this, this is say disconnected, then what quantity of current flow? So there is only path on the right comprise R3 and R4. So you can break up the circuit, put up this, and just simply divide E by R3 plus R4, you will get the current I2. Now you can add both the currents to get the total current. So this is I1 and I1 is this flowing this one this way, and I2 is flowing this way. Clear? So in this way we calculate. Next we calculated the potential of this point C. What is, if you, this is the potential at this point is 0, and this point has a potential of E. So if you go upward, the resistance of the branch increases. So as the resistance of the branch increases, the constant current I1 flows through this side. So according to Ohm's law, the potential drop will be the product of the current times the resistance. So if you go upward and upward, more and more resistance come into the path, and the potential drop will increase, reaching a maximum at this point. So we get the potential of the point VC, which is nothing but VC minus V0 is VC, I1 times R2. Okay, and we will have I1 is E over R1 plus R2. So this is calculated. Similarly, same footing here, potential 0, and the potential VD should be the potential drop due to the resistance R4 for a current I2. So this is VD I2 times R4. Clear? So that we have explained. So we got the potential of the point C, D, A and B, and also the currents I1 and I2. Then we compare that what is the potential of C and D are same. If it is same, then these 2 points will be balanced, and if whether there is a resistance connected between C and D or not, no current will flow. In that case, we will get a balanced bridge. So in case of a balanced bridge, the potential of the point C and D must be equal, and that means we have VC equals VD, means the bridge is balanced. For that condition, we must write I1 R2 equal to I2 R4, and again we have I1 equal to E over R1 plus R2 and E over on the right side R3 plus R4 times R4. You can cancel E, and cross multiplication will give you R2 R3 R2 R4 time equals R1 R4 and plus R2 R4. So these two terms cancels out and we are left with R2 R3 equals R1 R4. So what is, we got R1 over R2, R1 over R2 equals R3 over R4. This is the well-known condition for a balanced Wheatstone bridge. Clear? If the arm resistances are in the same ratio, that is R1 over R2 equals R2 R3 over R4, then there will be no flow of current between the points C and D and the bridge is said to be the balanced bridge, right? So this is the condition for this. Okay. Now again, if we want to extend, sometimes this is extended to know the power of this power dissipation in this branch when the bridge is unbalanced. Okay, in that case we have to consider that suppose there is a resistance, what we have taken as R5 say this is RL and the current is say IL, which we have already calculated. So the power across RL should be PL equals IL square RL. So if we know the current in the branch CD, so and again the VC minus VD is nothing but, we have already know VC and VD. So from VC and VD, the difference of the potential as we have derived can be used here to calculate the current I3 or IL, and that IL squared and multiplied to RL will give you the total power loss in this branch. And this power will be maximum for a particular choice of this RL. When this RL, the load resistance connected between the points C and D, equals the effective resistance of the circuit in the absence of RL, then the power dissipation at this between the load will be maximum. So the condition, this condition PL will be PL max when RL equal to RAB, right? This is maximum power transfer theorem. So I think that I am able to explain you the basic concepts involved in the Wheatstone bridge network. So I will request you, dear viewers, to put your comment, if any, on my chat box, and I request you to press the bell icon so that you will get the notification when new video is uploaded in the in my channel. So thank you very much for watching this video. This is the first effort, so it may not be so good, but I think I will improve if you cooperate. So thank you very much and good night.